Okay, the last section in chapter 4 that we're going to talk about is not going to have to do with polynomial or rational functions. Now we're going to look at polynomial and rational inequalities. So recall first solving a linear inequality, like negative 3x plus 6 less than or equal to 12. We could just approach this as if it were almost like an equation by subtracting 6 from both sides and then dividing by a negative 3. And recall that when you divide both sides of a linear inequality, you flip the sign, the inequality sign. So our answer becomes x is greater than or equal to negative 2. We can write that in interval notation from negative 2 to infinity, including negative 2, or also draw that on a graph. I'm going to go through two examples, one rational inequality, one polynomial inequality first, and one rational inequality after that. So first take a look at if we're going to solve x cubed minus 9x is less than or equal to 0, first we're going to take a look at the graph of f of x equals x cubed minus 9x. Yeah? If we take a look at this graph and we're interested in knowing where does it equal 0, it's looking like negative 3, 0, and 3 is where the graph equals 0. Where is it less? Well, from negative infinity to negative 3, and from 0 to 3, right? So we can look at our graph and determine the answer for this, but let me show you how to do it algebraically. The most important thing to remember when you're solving either a polynomial or a rational inequality is that you do not treat it like a linear inequality. I can't add 9x to both sides and then perhaps divide by x. Remember, dividing by x is not okay because we don't know its value. Could be 0, which would make the entire thing undefined. Could be a positive or negative. We don't know. Could flip the sign. We don't know. Okay? So that's not an option. So what we are going to do is we're going to solve it similarly to how we would solve a polynomial equation a little bit. Okay? And in fact, we're going to solve the related polynomial equation. What that means is just to replace the inequality sign with an equals. And if you remember how to solve polynomial equations, we're going to factor and then set each factor equal to 0. And then, of course, solve both resulting equations. So notice I get x is equal to 0 or x is equal to plus or minus 3. So what this is telling me then is that x cubed minus 9x is equal to 0 when x is negative 3, 0, or 3. So this is part of our answer. We saw it on the graph, but we also need to think about where is it less than 0. So we know what we saw on the graph, we know the solution, but how do we get it algebraically? All right. Well, what we do is we make something that we call a sign chart, which we've made already when we were looking at the behavior of a function near vertical asymptotes. So we're going to do it similarly. I'm going to draw a number line. I'm going to put all the values where my function is equivalent to 0, and I'm going to put a dot on each one because that's part of my solution, right? I'm interested in where it's less than or equal to 0, so those 3 x values are part of my solution. Then over here on the left, I'm going to list my function in its factored form. I'm going to separate my chart into 4 regions, and I'm going to set up some parentheses. So each one of these little parentheses inside each region is representing one of the factors of the function. Okay? I'm going to choose some values that are in the regions, so something from negative infinity to negative 3. How about negative 4? How about something between negative 3 and 0? We can do negative 1, x is 1, here, and then maybe x is 4. These values don't need to be very close to the values where the function equals 0 because we're not looking at what happens really close to that. We're looking at what happens in an entire region. So it's enough to pick any number that's in that region of the real numbers. Okay, plugging in a negative 4 to x, we get a negative. Into x squared minus 9, we get a positive. And a negative times a positive is a negative. Plugging in a -1, I get a negative and another negative, so a negative times a negative is a positive. Plugging in a 1, positive, negative, we get a negative overall. And plugging in a 4 gives us 2 positive factors, which leaves us with a positive function. Okay. Now remember, I'm looking for where where r of x, oh I'm sorry, I guess we didn't call it r of x. I'm looking for where x times x squared minus 9 is less than 0, right? That equates to negative. Okay, so in the two regions from, if I look at a number line to draw my solution set, oops, -3, 0, 3, I know that from -infinity to -3, I'm going to include it, right? And from 0 to 3, including both of those, that's where our function is less than or equal to 0. So there's a graphed solution set. I can put it into interval notation by saying -infinity to -3 inclusive and unioning it with 0, 3, including both the 0 and the 3. And then of course we could also write it just using inequality notation, saying x is less than or equal to -3, or 0 is less than x is less than or equal to 3. Alright, now I'm going to do one more example where I'm solving a rational inequality. We're going to solve x plus 1 over x minus 3 is greater than 2. Okay? Now, for linear and polynomial inequalities, we solved a related equation and kind of treated the inequality almost as if it were an equation to begin with. And in this problem, we're not really going to do the same thing, right? Part of the reason is if we were to solve this equation, we could just multiply by x minus 3 on both sides if this were an equation instead of an inequality. But the problem is we don't know the value of x minus 3. Could it be 0? Could it be negative? Could it flip the inequality sign? We don't know. So what we want to do is, the first thing, make sure that we are comparing some expression to 0. Because we're going to use the sign chart again, and we want to know again where it's positive and negative. And so comparing to 0 is equivalent to positives and negatives. Now since we can't multiply by x minus 3 on both sides, we have to find a common denominator between these two fractions because we are subtracting them. Our common denominator is x minus 3. And then we're going to put them together into one expression, distributing the -2, remembering that -2 times -3 is a positive 6. And then we're going to simplify both the numerator and the denominator. So we get -x plus 7 over x minus 3 is greater than 0. Okay, so that's the first thing, is to set it either less than 0 or greater than 0 depending on the sign that you're given in the beginning. Now we're going to talk about how we go about going further. So we're not really interested in our solution in where this might equal 0, but we are going to solve the related equation of -x plus 7 over x minus 3 equals 0, because it's going to give us the place where we're going to divide our sign charts. Okay, so this is going to, so the expression -x plus 7 over x minus 3 is equal to 0 when -x plus 7 equals 0, and that's true when x is equal to 7. But something else we also have to be really, really careful about. Since this is a rational equation, or I'm sorry, a rational expression, we know that x minus 3 cannot equal 0. So what that means is that x cannot equal 3. Okay, so when I set up my sign chart, those two important numbers, 3 and 7, are going to tell me something about when the graph might go above the x-axis or below the x-axis. So they're going to be our two dividing lines. All right, now We don't want to include 3 in our solution set, nor do we want to include 7 for 2 different reasons. We don't include the 3 because x can't equal 3, or the denominator would be undefined, or the fraction would be undefined. But we don't include 7 because, again, remember, we're not interested in where x is equal to 7 or where this inequality is equal to 0. We only have the greater than. So we're going to put a little circle around 3 and 7 to make sure we don't include them in our sign chart. And then I'm going to list my simplified inequality, the left side of my inequality over here on the left. Divide the sign chart into 3 regions. We're going to have one value in the numerator, one value in the denominator, for which we need to look at the signs. Let's choose a value here. I'm going to choose 0. I always like to choose 0 if that's possible. Let's choose 5, and then let's choose 8 over here. Alright, so if I plug in a 0 for x in the numerator, we get a positive and a negative in the denominator. So overall, that's a negative. Hold on, my phone rang. Now if I plug a 5 into the numerator, we're going to get a positive here and a positive in the denominator. If we also plug in a 5, overall that's a positive. Plugging in an 8, we get a negative in the numerator and a positive in the denominator, so overall that's a negative. Now remember what we were interested in looking for. We were interested in looking where minus x plus 7 over x minus 3 is greater than 0. So that corresponds to the positive region of the number line. Okay? So if we draw a number line, we're going to shade in between 3 and 7 on our number line. That corresponds to interval notation of 3 to 7, not including 3 and 7. Of course, we're going to use parentheses. Or we might also say that x is greater than 3, but also less than 7. Alright? Now, if we wanted to check this, maybe it's a good idea to take a look at the graph. So I have graphed it for us, and I'm going to take a look. It's on this graph here. Okay? Now notice between the region of 3 and 7, right? So 3 is about right here. It looks like this has an asymptote at 3, halfway between the 2 and the 4. And then right at 7, it's cutting over. Yeah? And it's equal to 0 right at 7, and then that's when it goes underneath. And over on the left-hand side in this area, it's all less than 0. Alright, so it looks like our solution makes sense, and good job.